Welcome to this Maths Made Easy video on integrating exponentials. And to start with, let's take a look at integrating the exponential function. Now we know if we differentiate e to the x with respect to x, then we simply get e to the x. So let's just denote this first. So if we differentiate e to the x with respect to x, then this simply gives us e to the x. Now we can use this fact then. If we integrate e to the x with respect to x, then that would simply give us e to the x again. So therefore, if we integrate e to the x with respect to x here, this simply gives us e to the x. And remember, as we don't have limits here on our integral, then we need our constant of integration plus c here. Now what about a more general result here? So for example, if we integrate then e to the ax plus b, so e to the ax plus b here, with respect to x, what would we obtain? Well, in this case here, what we'd obtain is 1 over a, so we'd obtain 1 over a times by e to the ax plus b here, and again, we need our constant of integration as we have no limits on the integral. Okay, you might also sometimes see this written as e to the ax plus b all over a plus c there. Okay. And then we take a look at an example here then. If we integrate e to the 3x plus 4, so what we're doing here now is integrating of this form here. E to the ax plus b, well in this case this is e to the 3x plus 4 then. So here now, again we just apply this rule here to simply obtain 1 over a, so that's 1 over 3, e to the 3x plus 4, and again, as we don't have limits on the integral, we need our constant of integration there, our plus c. And that covers integrating the exponential function. Moving on now to integrating to the natural logarithm. So generally, if we integrate x to the n with respect to x, well, this would give us x to the n plus 1, we just simply add 1 to the power, and we divide by the new power. Okay, and if we had no limits, we'd have our constant of integration there, our plus c. However, we run into a problem when n equals minus 1, because in this case, this would involve dividing by 0. So another function to integrate must be found, and this is the natural logarithm. So if we integrate 1 over x with respect to x, this would give us the natural logarithm, the absolute value of x. Okay. Again, if we had no limits, we would still include our constant of integration. And this rule also comes in two other forms. So if we integrate 1 over ax plus b, okay, with respect to x, then this is equal to 1 over a, the natural logarithm of the denominator here. Okay, so the absolute value of ax plus b. Okay, and again, if we had no limits, we do need our constant of integration there, r plus c. Okay, and if we have something of the form that looks like this, so this is the integral of f prime of x over f of x with respect to x, and this is equal to the natural logarithm of the absolute value of our denominator here, f of x. Okay, so absolute value of f of x. And again, we still include our constant of integration there. So let's take a look at some examples then. So let's change pen colour here for our examples. So let's say we want to integrate 1 over let's say 6 minus 7x. 6 minus 7x here with respect to x. Okay, well this will be equal to minus 1 over 7. That's minus 1 over 7 of the natural logarithm here. So minus 1 over 7 times the natural logarithm. Remember, this is the absolute value now of our denominator. Okay, what we've got here is something of this form here. Okay, so if we just highlight there, so we get minus 1 over 7 times the natural logarithm of the absolute value of our denominator, so that's 6 minus 7x. Okay, and again we have no limits here, so we do need our constant of integration, plus c. And let's take a look at another example here then. Let's say we're going to integrate 3 cos 3x, so 3 cos 3x, all over sine 3x. Okay, and we're integrating here with respect to x. But in this case now, notice that we have something of this form here. Okay, if f of x is our denominator, if we differentiate that, we get f prime of x. Okay, so we have something that's of this form here. So therefore we can use this result then, and we can write the integral then, or the result of the integral, as simply being the natural logarithm of the absolute value of our denominator here, sine 3x. Okay, so sine 3x. Okay, like so. And again, we have no limits, so we can't forget our constant of integration there. Okay, so that gives us everything we need there for integrating to the natural logarithm. And finally then, let's take a look at integrating partial fractions. So we're asked to integrate here 5x plus 4 over 2x plus 1 times by x plus 2. So here, first we need to get this into the correct form. We have two linear terms in our denominator here. So in that case, we can write this as, let's just use a different pen colour to highlight this. So this is a over 2x plus 1, and then it's going to be plus b, so plus b over x plus 2. And what I'll do is I'll just write these in brackets just so it's clear. Okay, 2x plus 1 and x plus 2 there. Now here, what we want to do first is get this over a common denominator, and then we're going to set the numerators equal to each other. And to do that, what I'd do here is times a by x plus 2 and simply b by 2x plus 1. So therefore, a times x plus 2 plus b times 2x plus 1 here is going to be equal to the numerator. Okay, so 5x plus 4. So here now, what I'm going to do is simply use substitution here to eliminate one of the variables, a or b, and then repeat that again to eliminate the other variable. So here, if we let x equal minus 2 first, so let x equal minus 2 then, what would we obtain here? Well, straight away, this a variable is going to cancel because we have minus 2 plus 2 giving us 0. So in that case then, we have b times by 2 lots of minus 2, which is minus 4 plus 1, giving us minus 3b there. And this is equal to 5 lots of minus 2, which gives us minus 10 plus the 4, giving us minus 6. So therefore, b is equal to 2. Minus 6 divided by minus 3 gives us 2. And here, if we let x equal minus a half then, so let x equal minus a half, that would eliminate this b term here, okay, because 2 lots of minus a half gives us minus 1 plus the 1, giving us 0 there. In that case then, what we obtain here is minus a half plus 2 times by a. So that gives us 3 over 2a, or 1.5a, and that's going to be equal to 5 lots of minus a half plus 4, which also gives us 3 over 2. And then in that case then, we simply obtain that a is equal to 1. So now let's write this in the correct form here by substituting in our a and our b here. So therefore, again using the correct colour here, this is going to be 1 over 2x plus 1, 1 over 2x plus 1, and our b is 2 here. So we write that in blue as well, plus 2 over x plus 2. Okay. Now what we want to do is we want to integrate this expression here, the part that we split up now, into partial fractions. So let's write this all now in a different colour so we can see clearly what we're doing. So therefore what we're looking for here is the integral of 1 over 2x plus 1 plus 2 over x plus 2 here. Okay, we're integrating all of this with respect to x. Now here, what we can do is we can split this into two integrals. So in that case, it's going to be the integral of 1 over 2x plus 1 here with respect to x, plus the integral of 2 over x plus 2 with respect to x. And now here, simply all we need to do then is obtain the correct form for integrating both of these expressions. Well, in the case of 1 over 2x plus 1, that would simply be a half of the natural logarithm of the modulus here for our denominator. So that's the modulus of 2x plus 1. Okay, so that's this first term evaluated here with this integral. We would also have a constant of integration here, but I will add that on at the very end once I've integrated this second expression. And now if we integrate this 2 over x plus 2 here, well, we could apply linearity here, and then we could write that as 2 lots of the integral of 1 over x plus 2 there. Okay, well in that case then that's going to give us 2 lots of the natural logarithm, again with our denominator here. So the modulus of our denominator, x plus 2. Okay, and then all we need finally is our constant of integration. And that gives us our result there for integrating 5x plus 4 over 2x plus 1 times by x plus 2. And that concludes this Maths Made Easy video on integrating exponentials.